All right, let's talk about trees. So last time we got through our BST conversation. We talked about insert and find and what a BST is and all that good stuff. But we had to rush the last few slides, so I want to slow down a little bit and cover these a little better. We talked about the in-order traversal, but it's worth a reminder. I only have one slide on it, and it's pretty important, specifically for task 6 for your coding. But if you do an in-order traversal on a BST, it will visit the nodes in sorted order. So it'll visit everything to the left, then the node, then everything to the right. By the definition of a BST, that will be sorted order. If you do that recursively throughout the entire tree, since the property of the tree applies to every single node, and an in-order traversal will visit the nodes in exactly that order, it will be an in sorted order traversal. It will be exactly in sorted order. So an in-order traversal on this tree is going to visit the nodes in exactly sorted order. So just a reminder on that one. I think I talked about that a bit last time. For efficiency, we had this one definition, a balanced binary tree. A balanced binary tree has roughly the same number of elements in its left subtree as its right subtree for every single node. And the example that we had in lecture is a fully balanced binary search tree. So that means the left and right subtree for every single node has exactly the same number of nodes in each subtree. As long as they're close, and specifically close within a constant, so if it's like 1 or 2 off, that's fine. But if it's a large number off, it's bad. That came out weird. There's mathematical definitions for bad in that situation. I don't want to go deep into it, though. But that's what a balanced binary tree is. And if your binary search tree is balanced, we get really good optimization from this. We get really good increases in speed. So the height of a tree, one more definition. The height of a tree is the distance from the root to any null value. And the height of a balanced binary tree is O of log n, where big O, this is our asymptotic notation. It means in the worst case. The absolute worst we can do is log n if it's balanced. And n is the number of values in the tree. So the number of nodes equivalent to the number of values, that would be n in this case. So if we have 7 nodes in our binary tree in the example in lecture, the height of that tree is log of 7-ish. The big O, the asymptotic notation, means we're ignoring any constants. So it could be 100 times log, it could be log n, it could be log n divided by 1,000. Whatever the constant is, we get rid of that and just say its order of growth is log n. Insert and find take log n, O of log n time. In our BSTs, if they're balanced, the height is log n. In our find and insert algorithms, each time we made a recursive call, we went down the tree by 1 node. So if we put log n calls on the stack, we go down log n height, then we have to reach the bottom of the tree. So our worst case, these algorithms are going to run in log n time, because that's how long it's going to take, how many recursive calls it'll take to reach the bottom of the tree. And each recursive call runs in constant time. There's a constant amount of work. Nothing in the recursive calls depends on the size of the tree. So it's constant time. It's some constant, but whatever the constant is, we just say it's a constant. It's constant time. And if we insert n elements, effectively we have another n log n sorting algorithm, so go us on this. We can take our n elements, stuff them all in a BST. Each insert takes log n time, and we inserted n things, so n times log n. We have our n log n sorting algorithm. So if you didn't like merge sort, here's another option. You get n log n sorting. Just stuff everything into a BST. But the more efficient, we already had sorting in n log n, so who cares? But the big advantage that we get from binary search trees is maintaining a sorted order, specifically when elements are being inserted and removed from the BST. If we can insert and remove in log n time, then we can maintain this sorted order in log n time as things are changing. In the example I gave, I had to rush it a bit last time, but the example I gave was a A leaderboard, you have like the million top scores for a particular thing. I don't know. And people are constantly changing their score. When they update their score, you would remove their old score from the tree and then insert the new one. If you can do both of those in log n time, which we can, not in 116, but you can, then you can update the tree in log n time while maintaining a sorted order. This is something we can't do with the data structures we had before trees. So if you try this with an array list, the worst case, big O is always the worst case. The worst case is that somebody who's not even on the leaderboard comes along and takes the top spot. You put them in index 0 of the array list, which means all n elements, everybody else in the array list has to be moved down by one index. It's going to take O of n time in the worst case. A linked list insert is extremely fast, O of 1, is asymptotically as fast as we can get, realistically. But the problem is it takes O of n time to figure out where to insert. So worst case, you have to insert at the end of the linked list, which we can fix that. We fix that with a queue by storing a reference to the front and back of the linked list. But even then, what if we have to insert something right in the middle of the linked list? Okay, we'll store a reference to that too. Okay, now first quarter, second quarter, like there's always going to be another situation where we're not going to have a reference to it, aside from storing references to everything, which is going to have its own problems efficiently. So if you want to insert right at the middle, you have to start at the beginning and say, get next, get next, get next, get next, get next, n over 2 times. That 1/2, the over 2 is a constant, so that's still O of n time, still linear time to insert, because you have to get to the spot to insert. And then when you want to insert, you just create a node and then update some references. That's constant time. It doesn't depend on the size of the list, but to get there does depend on the size of the list. So we could never do this before. If we wanted to maintain sorted order of data that's changing, can't do that with the data structures we've seen so far. So this is our advantage of a BST. This is why we would use a BST. So a lot of elements that need to stay sorted as they're changing. That's your application. You should be thinking, ooh, BST, I got this. And again, I think I mentioned it in this lecture as well as the other ones. If you don't have a lot of elements, like who cares? Just use an array list for everything. If everything in your application you have less than, I'll say, just making up numbers here, but if you have less than 1,000 things in your data structure, if n is less than 1,000, who cares? Do whatever. But once you have a lot of elements where you're going to feel the impact of this, that's when you want to use the BST. Crikey. So when we did our find with a BST, they've been working, I don't know what they're doing, they've been working out there for weeks. Hopefully they're done after spring break. When we did our find in a BST, we checked only 3 nodes. We have this tree with 7 values in it, and each time we do a check, we're moving down the height of the tree. The height of our tree is 3, so we checked 3 nodes to be able to find what we're looking for, or we would eventually get to null. The next step would be getting null and then returning false. So we checked 3 values out of a total of 7, which, big deal. Yeah, it's less than half, so that's good and all, but was it really worth learning BSTs to cut down that little bit of work? You would never notice the runtime difference of your tree checking all 7 nodes versus checking just 3 of them. Plus, we have some overhead with the BST. It might actually be slower once you add the constants back in. But what if your tree, and this is where we really started rushing last time, but what if your tree is 1,000,000 nodes? What if you have 1,000,000 nodes in your tree? And no, I'm not going to draw every individual node for this tree. 1,000,000 nodes. So with our previous tree, we have 7 nodes. We're taking the log base 2 of that, which is a little less than 3. If we had 8 nodes, log base 2 is exactly 3. So we're hitting the logarithm. We're right on track with that. But the power of logarithm is a very slow-growing algorithm. Power of algorithm is if we want to double the size of this tree, we're only adding 1 more to the height. If we want to add 1 more to the height of this tree, we can add 8 more nodes, 2 child nodes off of each of the bottom row in this tree. If If we want to increase the height again, we can add 16 nodes, then 32, 64, 128. We get a lot more nodes for each layer of height that we're willing to add to the tree. So if we go all the way to 1 million nodes, we have a tree, we want to store 1 million nodes in this thing. We know the height that we need to have. It's going to be the log base 2 of 1 million, which is just 20. It's actually a little less than 20. That's the height that we have to have of a tree to store 1 million nodes. In my example, I had to say it really quick last time, but the 20 questions games where you think of anything and it just asks you yes or no questions, the way that works is by building a binary search tree, or really a decision tree, but a binary tree regardless. A binary tree where each node is a question, and whether you answer yes or no, it's going to move left or right to another node, another node, another node, until it gets to the bottom of the tree, and then the node, instead of being a question, is going to be, oh, you're thinking of a book, and then it'll say the answer. It can have 1 million different answers, 1 million different things that you could be thinking of. I guess technically 500,000, right? 1 million things that you could be thinking of, and ask you 20 questions to be able to get there. And then when it goes into bonus rounds, it says, oh, give me 5 more questions, and it wants 25 questions. You have more than 10 million, oh, I can't do quick math today, 32 million, is it? Different things that it can be storing with those extra values, extra questions. Logarithm grows extremely slow, or the other side, exponentiation. An exponential algorithm grows extremely fast. So the opposite of log is exponentiation. The height of the tree to the number of nodes you can store is exponential growth, which is extremely fast. If the tree is balanced. So those are big ifs. If the tree is balanced, if the tree is balanced, if the tree is balanced. If the tree is not balanced, we can be in big trouble. So here, we were very careful in the lecture example to insert the nodes in the right order. Like in the repo, we're inserting the nodes in the right order to make sure that it is balanced. All the slides, I use balanced trees and all that. But what if it weren't balanced? In our implementation is actually an O of n implementation, because the worst case, we're going to get this. So if we insert the values in sorted order already, we're going to insert -3, that's going to be the root. We're going to insert 2, our comparator says go to the right. We're going to insert 4, our comparator says go to the right. Comparator says go to the right. We reach null and insert there. 5, right, null, insert. 7, right. All the way to 14, it's going all the way to the right. So we're always going to the right if we're inserting in sorted order, which effectively gives us a linked list. We get O of n everything on this. So that is a big if. We would have to be extremely careful the way we insert things to be able to maintain the balanced property of a binary search tree. We maintain the property of a binary search tree, so we make sure it's still a binary search tree, but we don't do anything about the balance. So we do lose all of our gains, which is the only reason to use a BST is for the efficiency, and we lose it all in our implementation. So our implementation kind of sucks. So how would we insert into a tree and keep it balanced as we're inserting, no matter what order we insert in? And something we don't really talk about in 1.16, but how would we remove a node and maintain the sorted order and maintain the balanced property of the tree? And then duplicates also is always a concern. How do we handle the duplicates is always a good question. So all these questions and more, CSE 250's got you covered. You'll learn something called self-balancing binary search trees. And that is going to get all of the properties that we want. It's going to give us log n insert, log n removal, log n, maintain the log n find because it's going to stay balanced. Not necessarily fully balanced, but it will keep it balanced within a constant of log n. So we can get our efficiency out of it. And the way it works, just very roughly, you'll learn all the details more than you've ever wanted to know in CSE 250. But roughly how it works, you'll insert -3, it'll be the root. You'll insert 2, everything's fine. And when you insert 4, and things start getting a little imbalanced, it might actually be when you insert 5. But for the sake of example, when you insert 4, the algorithm's going to start noticing that, hey, this is getting pretty imbalanced. and it's going to restructure the tree through what we call a rotation. So it's going to rotate so that 2 is now going to be the root node, 3 will be its left child, and 4 will be its right child. So it'll restructure the tree as you're inserting by detecting when things get imbalanced and then rotating to keep them more balanced, closer to balanced. And that's how it's going to keep that balanced structure. And then similar thing when you remove a node, deciding whether the left or the right child is going to replace that node, which one to rotate up, is going to depend on that balance. And that all has to happen in log n time. If that rebalancing is too slow, if it gets slower than log n, again, we're losing our efficiency. So all that rebalancing has to happen in log n time in the worst case. So all good stuff that you're going to learn in CSE 250. You're going to learn I think they still teach both ways, the red-black trees and the AVL trees, 2 different self-balancing binary search trees. Loud. Any questions on this? I'll hear that beeping. It's not just in my head, right? Okay, really no questions at all? All right. Let's do some coding. So let's see some of this BST stuff in action, and we should have time to go into the debugger and get some more debugger practice. Can never get enough debugger exposure. And there's something I realized I might have missed or not explained very well last time we were in the debugger. Somebody mentioned in last class, so yeah, maybe it was me that was beeping. I might be low on batteries. I am actually. I'm covering for Paul, so I did his morning lectures, and I'm doing my 4 lectures, so it'll be I can't even do math, a 6-lecture day today. I'm going to be exhausted by the time I'm done with all this. So let's do some coding. So we want to see a BST in action. What I want to do today is sort health potions in decreasing order according to the amount of health that will recover by consuming one of those potions. That's what I want to do. I want to build that functionality, and we'll build it all today. So one big misconception that I've been seeing with the homework already with task 6, those of you who have started task 6, some of you have had this question, or not this question, but this mistake, I guess, is that y'all want to change the BST code itself. So when I say create a BST of song, they'll go like this and start changing this to a BST of song. Do not do that. It's not going to do what you want it to do. Remember, this is a variable name, by the way. This A is a variable name. We can actually change this. If I refactor this and rename this to song, I mean, that works. But now my generic type variable name is just song. It's not the song class. It's just like if I created a variable and named it song. It doesn't change anything with any of this code, and is absolutely not what we want to do. But this is just a variable name. We tend to use the 1-letter names. Like I can name this whatever I want. It's just a variable. We can name it whatever we want. But we tend to stick to the, and by the way, I'm using refactor rename. That'll rename all instances of a variable name, which is pretty handy. But we name it one single uppercase letter just because that's the convention. That's what you'll see in industry. That's what other developers would expect a generic type variable name to be named, one uppercase letter. So we name it one uppercase letter. This BST is written, comparator can be final, is written with a generic type and a comparator for that type. These two things make this code completely generic. We can use this BST code for any type with any comparator for that type, which means this code is done. We don't have to do anything here. BST code is done. For your homework, you can take BST, binary tree node, and even the comparator, Control C, go into the data structures package of your project. Control V, paste them. That code's done. You don't have to touch them. We gave it all to you. We went over it in lecture. There's no need for you to rewrite that code or do anything with it. Those classes are done, and you don't have to modify them at all. So don't fall into the trap of changing any of the BST code. It's all here for you. It's all ready for you. Take it. We're giving it to you. It's your code. It's our code that we're giving to you. You can use it however you want. So we're going to use that code, and I'm going to create a new package to keep things a little organized. I was going to call it example. So I right-clicked new package. I don't think you've had to create a new package yet in the project. So new package. Then I'm going to go into this package and create a class that's going to hold our code. I'm just going to have one method in there, and it's going to be a main method. It's usually common to call the class main when you're doing that. So main, I'm going to have a main method, and this is where I'm going to write my code. So I want to use the BST class. I'm not changing any BST code, but when I create my BST, it will be a BST of health potion. This is when I'm going to say, this is what A is for this variable. For this BST, replace A with health potion. So that's where you would create your BST of songs, is when you actually start using the BST in your playlist class. You don't change the BST code at all. So we have our health potion. Let's get rid of the errors here. Whenever you're importing, sometimes you'll have a choice. If you're importing using IntelliJ, you'll have a choice of classes. If there are multiple classes with the same name, please be mindful of this, be careful of this, and choose which one you use carefully. This is one case where I kind of regret showing the IntelliJ shortcuts, because some of you are using them without thinking about it too much. But if you're having it import for you, make sure you import the right one. We're going to talk about health potions again in week 9. I don't want that one. I want the week 6 version. So I'm going to import that one. BST, there's only going to be one choice. So it's just going to import it without giving me a choice. But whenever there's a choice, choose the right one. Choose the one that makes sense for what you're doing. I'll talk about that in actually pretty soon. Create a new BST. And the BST takes a comparator that I don't have right now. So let's write a comparator for this. Yeah, wouldn't that suck? In the middle of lecture, my brain just has to auto-update. I feel like it does sometimes when I just can't think of something. It's just updating and restarting. Would the quiz and interview results be up before we come back from spring break? They should be. They should be. The TAs, I assume that they're on track, but they should be following the same schedule, just treating it as though you had lab next week and getting them done before your lab would be if you had lab next week. That's what I would expect them to be doing. So they should be, the results should be in. If not, it's Paul's fault. Paul always blames me in his lectures, so I got to blame him in his own lectures today. That was fun. But we need an instance of a comparator. So let's create a comparator that's going to compare health potions the way we want. So I'll call this health potion comparator, because what else am I going to call it? And I'm going to have this extend my comparator. And when we're extending the comparator takes a type. We're going to specify that type in our extends line. We're not just going to extend comparator, we're going to extend comparator of health potion. My goodness. There we go. We're going to import health potion. I'm going to choose the right one. And here's where that becomes very important in what I'm seeing on homework. It's a common mistake. I do expect this each semester. But a frustrating one for the student nonetheless. So if you avoid this one, there is a java.util.comparator. There is a built-in Java comparator class. I've never used that in lecture. I've never talked about it. I never even mentioned it until now. There's no reason you should be importing that one. So whenever I see that one imported, I know what happened. You just said, IntelliJ, do my code for me, and then IntelliJ imported that one. And you didn't really think about your imports, which is one thing I regret saying, oh yeah, IntelliJ's got your back, and there's some shortcuts that it can do for you. This is one where you can get in trouble. When you have a list, or if you didn't paste in the comparator class into your data structures package in your homework yet, or if you named it the wrong thing, I saw that one as well, or if you named it wrong, IntelliJ's auto import is going to grab you the java.util comparator, which is nothing we've ever talked about in lecture. It's never mentioned in the homework doc. There's no reason to ever have that one. So we want to make sure we import the right comparator, which is the comparator. Again, you take this code from the repo, you copy it, you go into your project. You go into your project. You go to data structures, and you paste it. That's it. You shouldn't be doing anything else. Wait, I kind of want you to ask again. That's it. Binary tree node, BST. Here, I'll start task 6 right here. Go to your data structures package, Control V, boom. Sure, add them. IntelliJ even updates the package for us. We don't want these. It's not week 7. Oh, there's a little bit to do, I guess. It's not a week 7 binary tree node. It's a data structures binary tree node. Ugh, why has it got all this week 7? Week 7. Week 7. IntelliJ added all that for me. I don't want any of that. Probably because I pasted them at the same time. I don't think it would do that if I pasted the binary tree node first. And the examples can go. But you just paste that code. And then there's no misspellings. I saw somebody where this was called compare. I don't know why they typed compare instead of comparator. Again, I always recommend cut and pasting. Whenever you have a name that has to be exact, either cut and paste it like I just showed you there, or cut and paste it from the homework document when that's not an option. Make sure you don't have any typos. But anyway, let's get back to it. So my health potion comparator is going to extend comparator, which means I need a method called compare that satisfies the comparator. So if I have public Boolean, actually let me do it this way, compare health potion, potion 1, health potion, potion 2. In the TLDR, that is, if IntelliJ is writing code for you, at least make sure it's writing the right code. Understand the code that it's writing. If you don't understand the code that it's writing, that's its own problem. And I want to return. I want to sort these in decreasing order according to their increase variable. So I'm going to have to go to the health potion class. We never wrote a getter for increase. So I'm going to write my getter, public int get increase, return this dot increase. Get increase, I'm going to use greater than to sort in decreasing order. Potion 2 dot get increase, semicolon. And here's where the override annotation, I recommend this a bunch. Paul doesn't use it at all. He didn't use it in lecture one time. Students got asked about it in the interview, and then they said, Paul's never even used this at all. I've never seen it. I don't know what it is. I recommend it. One day we'll get Paul using it too. But using your override annotation. This is telling the compiler that, hey, I'm intending to override 2 R's. I'm intending to override a method here, and I'm going to get an error. What the override annotation does to help you out is I'm saying, Java, I'm overriding something. If you're not actually overriding something, it's going to yell at you and say, hey, I think you better take a look at this. If I don't have this override annotation, everything just runs as intended, or not as intended, but it runs without crashing, but I didn't actually override anything, the override annotation is going to tell me that, hey, you're not overriding anything. Method does not override method from its superclass because I have this spelled wrong. One little error, if you're not using your annotation, one little typo can throw off everything and make all your code broken and be a really frustrating thing to find out. That's a tough one that's eventually going to have you saying, man, I spent hours on something so stupid like that. Just to have your annotation, and that's one silly mistake that can't cost you hours. It's going to cost you seconds. The compiler is just going to catch it for you. So we have our method. Everything's looking good here. And you'll get this symbol, too, if you're overriding. This is Paul's defense. He's like, well, I'm just going to look for that symbol to see if I'm overriding something. With this being spelled wrong and no annotation, that symbol's not there, and he says, well, I'll just notice that the symbol's not there. I don't know. That's not great for me. One, if you're not using IntelliJ, you're not going to have that symbol. And two, I'm going to forget to check for that symbol at least once in my career, and the override annotation is going to save me. Okay, so we can go back to our main method, new health potion comparator, and we have our BST set up. Did I finish that conversation? So the comparator, say we import the Java one, and I'll see this in the code, and I'll say, why did you import that one? And the student will always go like, I don't know. And I'll say, you had IntelliJ import it, which there's nothing wrong with that, by the way. But if IntelliJ is importing it, double check what it's importing and make sure it's right. This is always not what you want. In CSE 116 specifically, we're not going to use Java's comparator class at all. Make sure you're importing the right one, which should be the one in your data structures package. So now that we have our BST set up, we're ready to insert into this BST. So when we insert, we have to remember, okay, which way did the comparator go if it says it's before it goes to the left, left. If it comes after, go to the right. And you have to remember all that stuff when you're doing your homework, right? No. You already have an insert method. We covered it in class. We'll ask you about it in the interview, sure. But we already gave you the code for it. Just call insert. You're already done with insert. So when you're inserting new songs into your BST, just call insert. Throw those songs in that sucker. You already have your comparator from task 5. I know a lot of you are working on task 5 still. But you'll have by the time you're on task 6, you'll have your comparator written from task 5. You have the BST written from class. You have the insert method written from class. A lot of the stuff's done for you already by the time you get to task 6. Task 6, the bulk of the work, really the only thing we're truly asking you to do is the traversal, doing an in-order traversal and converting the values of the BST into a linked list. Which even that, it's not too much code, but it will take you a while to design and to think about how to approach the problem and figure that one out. It's more of a design problem, though, than a coding question, which is a nice change of pace, especially after task 4. Task 5 is pretty light, and then you get a design question instead of a write a bunch of test cases question. So, but the rest of the homework shouldn't be any work. So we're going to insert a new health potion. I'm just going to put them at 0.0 last time. Let's put it 5.0, 10.0, 10.2. I don't know. What's important for us here is the increase value. So let's create a health potion that increases our health by 10. We'll put them all at the same location. Why not? Maybe they're all in a player's inventory and the player's at this location. We're going to insert one with a value of 5, 7. We'll have a really small potion with 1. We'll create a potion with 50, 100, and 6. Sure. And then we can do an in-order traversal on this. I won't talk about the in-order traversal too much, but that's, of course, the bulk of what you're expected to do in task 6. But we would do a sout bst.getroot.inorder traversal. on, and we have this set up in a little bit awkward way, but we'll get the root again as the parameter. This should have a method, an overload method that takes no parameters, and then a helper method that takes the root. Would have been the better way to set that up. But we didn't, so I'm not going to worry about it. But we're going to call our in-order traversal. You have to completely rewrite in-order traversal anyway for your homework. But we'll traverse them to make sure, at least verify that we're storing these things in the right order. And in-order traversals should iterate over these things, visit these things in sorted order. So it should go in decreasing order. Is what we would expect. And let's look at our health potion class. There's one thing I want to change here. The health potion, we'll have it say health potion still. And then the toString method that we wrote doesn't actually print out the increase value, which is the only one we're interested in for this example. So let's do this dot increase plus, close that thing. Just so we can see something happening. And then we can run this code and verify that the tree is actually doing what we want it to do. That an in-order traversal on the root of this tree is going to visit the health potions in decreasing order according to their increased value, the amount of health that they restore. So we get the health potion with 100, then 50, then 10, 7, 6, 5, 1. So success. Our BST works. Our in-order traversal does visit them in sorted order. Everything's looking good for us here. And the next thing I want to do is the debugger. So anybody have questions before we start stepping through a debugger? All right, let's get some debugger practice. So I'm going to set a breakpoint. I'm just going to set it on the first line so we can step through everything. Hit the debug button. Let's get into it. So the very first thing we do in the main method is we're going to create the health potion comparator. So remember when we talked about these comparator classes? This comparator has no defined constructor in our code. That means it gets the default constructor, which has no parameters, no lines of code, and then an implicit superconstructor call. So the constructor, it's not doing anything, but it has a reference to the object being constructed, a health potion comparator at 449. And if we step into, we actually end up at the comparator class. So we do have both constructor calls on the heap, the health potion comparator constructor. It extends comparator, so comparator is going to have its own constructor call on the stack. Even though there's no constructor code for either of them, we do get the default constructor calls. Remember, I went through that in the memory diagram. We had these calls on the stack. I wasn't just making that up. We can verify right now the debugger has my back and says, oh no, those constructor calls definitely go on the stack. So we can see that actually in action. That is how Java works. That is how our code works. We do get those constructor calls on the stack, even though they don't do anything particularly useful. They just initialize everything, which we don't even have any instance variables here, so they really don't do anything at all. But we have this constructor call of comparator, which has a health potion comparator at 449. That's the same exact reference that we have in the other constructor. We're only creating one object, and it is of type health potion comparator. So even though we're in the comparator's constructor, we are constructing an object of type health potion comparator. And I think, be a little experimental here, but if I click force step into, we should get, hey, we did. We should actually get to the object constructor call. That's internal to Java, so we're never concerned about this in our memory diagrams. But the object constructor is actually called as well. And we can see that call going on the stack as well. If you don't do this force step into, it's only going to go over code that we care about. We're not going to get internal code to Java. But if you do force step into, if you're ever curious what's happening inside Java, you can click that for what it's worth. But that verifies a lot of things, that we do actually extend object, and that the object constructor is being called as well. We can even look at the methods in here. Since we're here, we'll take a brief detour. Here's our toString method that we've inherited from the object class. Equals more of a detour than I wanted. And the equals method, it's just going to use the equal operator to check if those two values are equal, which is going to compare them by reference. So if we call equals, it's going to give us the default, just check the references. But we don't really want to be in there, so I'm going to do step out, so we just get right out of the object class, get back to code we care about, and we still have our two constructor calls on the stack. The comparator constructor call returns, the health potion comparator constructor call returns, and then we return a reference to the object that was created, bless you, to the stack frame that called it. And then that is an argument for the BST constructor. So the argument comparator gets that health potion comparator at 449 that was just constructed. And the big thing, the thing that seemed to blow minds in the last lecture, something I must not have highlighted much last week when I did the debugger, or 2 weeks ago. That was 2 weeks ago now, wasn't it? Is this is showing all the stack frames and all of the variables that are inside that stack frame. The thing I didn't show much is this arrow right here means that this variable is storing a reference to an object on the heap. And if you click the arrow, it'll show you the instance variables of that object on the heap. That arrow is effectively saying, take me to the object to which you refer and show me some things about that object. So if you expand these, you can see what's in these values. The comparator doesn't have anything in it, but the BST that's being constructed right now has a root and comparator instance variables, which are the two variables that are being initialized right now. So comparator equals comparator. We're going to see this dot comparator set equal to this comparator at 449. So that this dot comparator gets that 449 comparator, a reference to it. Root is still going to be null for now. And then we get that BST on the stack stored in BST. And again, in this main stack frame, we can expand this to see the instance variables of that particular binary search tree. So the arrow means take me to this object and show me its instance variables. Everything at the top level, these are the variables in that stack frame on the stack. And you can use this list. This is all the stack frames on the stack, where the top stack frame is the active stack frame. And that'll show you all the variables in each stack frame. So all the same information that we do in our memory diagrams, but in a little bit different representation. And then when we get to a case like this, is the BST code class given to us in the task 6 instructions? The answer of yes, it kind of is. The instructions tell you to go to the examples repo and grab it from there. So I don't explicitly give it in there, but I tell you where you can find it. But it says right in the instructions, just copy and paste the stuff. Just grab it from the repo. So when you get to a case like this is one gripe that I do have about the debugger. The debugger saves our lives in many ways. Saves, I shouldn't say lives, but much time in many ways. But this is one case where it just falls a little bit short for me. When you have two method calls in the same line, sometimes it'll get in a state like this, where if you click step into, it'll choose one of those method calls and go into that method call. But it won't always choose the one that comes first. It won't just go into the first one. That's one of my gripes. Just go into the first one. In this case, if I click step into, it's going to go right into the insert method and completely skip the health potion constructor call. But if you see this, you can click on the one that you want to go into and then see that call, that method call, and go into that one. So we'll go into the health potion constructor. we have the stack, all of our variables on the stack, and then it knows that we're about to use this dot increase, so it's showing us this dot increase explicitly without us having to go to the heap. That doesn't mean that there's another variable on the stack, though, in this stack frame. It's just showing us what this dot increase is because it can see that we're going to use it. But we can see on the stack we have these values, and it's letting us know that this is the object being constructed, so don't take this at face value yet. These values will probably be replaced soon. We have the super constructor call, so we get into the game item constructor. It's going to handle the location stuff. We're going to replace this .x location, this .y location in this 453 with the values from the constructor. And now back in the health potion constructor, we can see those instance variables have changed. We're at 453. This is the same object. The two constructors are initializing the same object. And then we set increase. Increase gets its 10. And then we're done with the constructor. We can return. And then we can call insert to insert this value into the BST. This dot root is null. So we're going to insert this value as the new root binary node. At this point, we've seen the binary. Actually, have we seen the binary tree node constructor yet? Not in this example. So the constructor is going to set our left, right, and value. So we created this node 707. This dot value is that health potion, and we can see the values of that health potion. And that's going to be the new root of the BST. We're going to set the root of the BST equal to that node. So our BST has a root 707 with a value, which is the health potion, with an increase of 10. At this point, I want to skip some of these so we can see the structure of a tree. So I'm going to do step over, skip some of them, and we'll get right to the last one. So when we're at the last one, our BST, we can keep expanding this to see what the BST looks like at this point. Our BST has still the root 707. That root has a value 10. Its left has a value 50, a right of null, and a left with 100, and null, null. The root's right has the value 5. Its left has the value 7, and null, null. Its right has a value 1, and null, null. So we can see the whole structure of the tree by continuously following the references, by following those arrows, by clicking those arrows. And then when we insert 6, we're going to call the comparator a few times. We're going to go down the recursion. We're running out of time, so let's just get to... Oh, I'm clicking through way too much.